Welcome back to second lecture on internal flow. This lecture we are going to discuss some of the minor energy losses occurred in the pipe flow. So minor energy losses includes the following cases because of these are the causes due to which the minor losses occurred in the pipe. That is loss of head due to sudden enlargement. So if there is a sudden enlargement happens, then minor losses occur. Because due to sudden enlargement, there is a sudden change in magnitude. Then sudden contraction means sudden reduction in sudden increase in velocity. Then loss of head due to obstruction in the flow passage. So like walls, there is obstruction in the flow passage because of opening and closing of the wall also that the energy loss takes place. And loss of head at the entrance of the pipe. So this is exit, this is entrance. So loss of head at the exit of the pipe, because suppose if it leaves this particular tank or pipe, so its velocity uh, it, it varies. It maybe decreases. It is a pressurized fluid, so if it releases to the atmospheric pressure, so there is a change in velocity when it enters into the pipe as well as it leaves exit from the pipe or exit from the tank also. So loss of head at the entry or exit, and loss of head due to bend in the pipe section. So such kind of bends, there are many bends are there in the pipeline. So because of this bend also, there is a possibility of loss of energy. And the loss of head in various pipe fittings. So again, due to gradual contraction or gradual enlargement also, the loss of head occurs. Various pipe fittings, that is in between, there are various fittings are there. Maybe pressure tapping is there, some temperature settings are there, or in between some enlarger reducers. So these are the various pipe fittings. So due to pipe fitting also, there is a lot. So one by one we'll discuss this loss of head due to sudden enlargement. So if these are the two sections, if we apply the knowledge equation, so due to sudden enlargement, these losses are generally calculated by using this formula. Is V1 minus V2 bracket square by YG. Loss of head due to sudden contraction. Now here only we consider the higher of two velocity, that is the maximum velocity, that is at V2. So V2 is measured at some distance from the vena contract, not exactly here. So when the fluid becomes streamlined, then the V2 is measured. So it is K times V2 square by twice G is exit losses, where K is calculated by using this formula where Cc is the coefficient of contraction. And if the value of Cc is not given, then the loss coefficient is considered, then K value is considered as 0.5. This is loss due to sudden contraction, we can say. 0.5 V2 square. So due to sudden enlargement, that is both velocities are considered, that is V1 minus V2 brackets. This is sudden enlargement, and sudden contraction we have 8 times V2 square by 2g or 0.5 V2 square by 2g. The loss of head due to obstruction in the pipe. Figure shows the loss of energy due to obstruction. So there are many obstructions are there in the pipeline. So due to that, there is a reduction in cross-sectional area of the pipeline, and by presence of the obstruction, which is followed by an abrupt enlargement or reduction in the cross-section, the stream beyond the obstruction, the head loss due to obstruction is given by this relation, where capital A is the area of the cross-section, small a is the area of the obstruction, and this is the coefficient of contraction. Here the mean velocity is considered. This is obstruction losses. So is the area of the pipe, maximum area of the obstruction. So maximum area is to be considered. Is the velocity of the liquid in the pipe. Then loss of head at the entrance of the pipeline, which is same as the loss due to sudden contraction. So HI is equal to 0.5 V square by 2H is this. Loss of head at the exit of the pipeline, which is given by HO is equal to V square by 2H. So that is exit losses. Where V is the velocity at the outlet. And loss of head in the due to various bends. So K into V square by 2H, where V is the mean velocity of the flow of fluid. K is the coefficient of bend. It depends upon, again, angle of the bend, radius of the curvature of the bend, and diameter of the pipeline. So in the experiment that is minor losses, we are going to study this, how the losses K value varies with the bend angle or curvature or the diameter of the pipeline. This is due to bend. So for every bend, maybe it is short bend, it is steep right angle bend, long bend. So for each bend, the K value is different. This is loss due to bend, and the K value is obtained experimentally. And loss of head in various pipe fittings, so such as walls, couplings, etc., may be represented by this. H fitting is equal to K into V square by 2H. Where V is the mean velocity of flow in pipe, K is the value of coefficient. It depends on the type of pipe fittings. That's it from this particular session. At the end of the session, you will be able to describe causes of minor losses and their expressions for calculating the same. Generally, in most of the numericals in this particular syllabus, where we neglect the minor losses. So numerical part, even if some derivations will consider the expression of minor losses. But as far as the numerical part is concerned, it is not required. But while deriving some expressions, sometimes we use these expressions. In practice, minor losses, if there are large number of fittings are there and various bends are there, then we have to consider. The length of the pipeline is not very long, maybe within 1-2 meter. Then in that case, we cannot neglect the minor losses. We have to consider minor losses as well. Most of the practical irrigation systems, generally for calculating the pumping power, these losses we generally calculate how much energy is required to overcome the frictional losses, because pump power is mainly determined with the help of head required, and head is generally what is the elevation from the ground, that is the potential energy to be raised, that is one major head. In addition to that, the friction, various losses occurred in the pipeline, maybe major losses, minor losses. So all these losses are added in the total head, and the pumping power is then determined, that is P is equal to gamma Q H. So that H constitutes all the heads. So major head, that is the pumping head, that is required to raise the potential energy of the fluid, and other losses, then H plus HF plus HL plus suction head, delivery head. So entire head is called as a manometric head. So that head is then used for calculating the pumping power. Accordingly, the pump is selected. So every pumping system or designing of any pumping system, we require this knowledge. That's it from this session. Thank you very much.